Welcome to video number 4 in the coupled oscillator series. Today we're going to look at a Lagrangian approach to solving coupled oscillator problems. So we'll stick with, for now anyway, with the simple 2 quartz 3 spring problem that we've already studied fairly extensively. So you should probably remember that when you do Lagrangian problems, the first thing you start with is write down the kinetic and the potential energies. And in this case, that's pretty simple. You first write down the kinetic energy, which is just going to be the kinetic energy of the quartz, because we assume that the springs are massless. So that's going to be 1/2 mx1 dot squared, 1/2 m1 x1 double dot squared plus 1/2 m2 x2 dot squared. The potential energy is going to be the potential energy of the spring, the elastic potential energy of all the springs. So that will be 1/2 for the left and rightmost spring. And the central spring will depend on the difference in the position of the 2 quartz. So there we get So that's the potential energy. We'll rewrite it a little bit like this. Which just amounts to grouping terms together so that all the x1 squared, x2 squared, and x1, x2 terms are grouped together. Okay, so the Lagrangian, we know, is the kinetic energy minus the potential energy. And the Lagrangian equation, of which there will be 2 here, because we have 2 variables, 2 coordinates, x1 and x2, look like this. And since the Lagrangian depends on t minus u, t is the only quantity that depends on x1 dot and x2 dot, and u is the only one that depends on the x1, x2, and x3. With x1 and x2 without the dots, we then get and that just gives us just by taking the derivatives of t and u with respect to x1 dot and x1. And then we'll do the same thing for x2. And if you look back at your notes, you'll find that these 2 equations are exactly the same ones that we found using Newton's second law. That's no surprise. Of course, the physics is the same. But the Lagrangian approach obviously works as well. There's no intrinsic advantage in using the Lagrangian approach here, but there will be if we work in cases where the situation is a bit more complicated. So let's take a look at such a situation. So here we have a double pendulum. So we have one mass that is attached to a rigid rod that we take to be massless. The rod makes an angle phi1 to the vertical, and it's attached to a fixed point here on the ceiling, and the rod has length m1, and the mass is mass m1. Then we take a second pendulum attached to the first one, so that we get this double pendulum structure, and we use a similar notation here. The length of the second pendulum is L2, the mass at the end is m2, and the angle that this pendulum makes with the vertical is phi2. So now what we need to do is calculate the kinetic and potential energy of this system. We can start with the kinetic energy. The first thing we need to do in order to calculate the kinetic energy are the velocities. And we need to write the velocities in terms of the generalized coordinates here, which are angles, not positions. So that means for the velocity of mass 1, we get the following. So that's quite simple. The motion is in the direction of phi 1 hat, because phi hat is in this direction, the direction that the pendulum moves when phi 1 changes. The second velocity is similar. We know that it's going to be, the velocity of the second mass is going to be the velocity of mass 1 plus the velocity of mass 2 relative to mass 1. The velocity of mass 1, we already know what it is, and then we do the same thing for the second pendulum that we did for the first. So we get here L2, phi 2 dot, phi 2 hat. And those are the two velocities. It's not entirely easy to work with these, but we don't have to, because we're trying to calculate the kinetic energy, so we can just work with the squares of these. And we know that the square of V1 is then just going to be L1 squared, V1 dot squared, and the square of V2 will be slightly more complicated because it is just this. Okay, and we can relatively simply calculate that. We just have to substitute now the values for V1 and V1 square in here. Like that. So now we want to find out, the one thing we need to calculate now is what the scalar product is. The scalar product of phi hat with phi 1 hat with phi 2 hat. So we know that the scalar product of two vectors is the product of the magnitude of the two vectors, which in this case is 1 in both cases, times the cosine of the angle between them. Okay. Now to figure out what the cosine between them is, we just have to note that the angle between phi 1 and phi 2, the angle between the two pendulums, is just phi 2 minus phi 1. It's supposed to say phi 1 there. Phi 1. So phi 2 hat, scalar phi 1 hat, the angle between the those unit vectors is going to be the same as between the pendulums, even though they're turned by 90 degrees. So that's 1 times cosine of phi 2 minus phi 1. That then allows us to write down the complete expression for the kinetic energy. So T equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And then if we just plug everything in, we get the following after a little bit of work. The reason it's m1 and m2 here is, of course, that L1 squared phi 1 dot squared exists both in v2 squared and in v1 squared. That's the first term. Then we get There. So that's relatively complex, but that is indeed the full expression for the kinetic energy. Okay, next thing to calculate then is the potential energy. And it's a gravitational potential energy here, since we're dealing with pendulums. So we need to know the height of m1 and m2 as a function of phi1 and phi2. And that's relatively simple. In the case of mass 1, we just get that that's the height of this pendulum above its lowest position. For y2, it's the same thing. Except we must now also add in the height of m1 because mass 2, pendulum 2, is attached to mass 1. Okay. And this then gives us the potential energy. It's the potential energies of the two masses, knowing their vertical positions. Then we just have to substitute, and we obtain there. Okay, so that's the potential energy. Now the problem with these forms is that they're transcendental in the angles, meaning that they would depend on cosines, which means that the Lagrange equations are going to be severely nonlinear, and so we can't solve them. Now to resolve this, we're going to use an approximation, which simply amounts to saying that cosine of phi I equals 1 minus phi I squared over 2, plus other terms then on the order of phi to the fourth, but if phi is small, they're not going to matter. Before applying this, we're going to move things around a little bit here to make some more space. All right, so if we apply this approximation now to both t and u, we'll get the following. There. So now we have both the kinetic and the potential energy on quadratic forms in the phi's and the phi dots. So this will then ensure the linearity of the Lagrange equation so we can come up with solutions. We'll take a break here in this video to make it sure it doesn't get too long, and we'll continue this problem in the next video.